Welcome everyone to the Waterloo Data Science and Data Engineering series. Today we'll be talking about the distributed computer, building a future-proof distributed systems. We have Wes Garland, who is the CTO of King's Distributed Systems, who will be talking about the distributed computer. And along with him, we have Hamada Gasmala, who is the AI task force lead at King's Distributed Systems as well. Wes is a veteran in the software industry. He is a developer, a software developer, a product manager, team leader with more than 20 years of experience in the industry developing successful products in the telecom, gaming, real estate, publishing, and mobile space. His interest includes server-side JavaScript platform development, and he's been a member of the Securable Modules working group, which eventually became the CommonJS. He is a primary author of GPSEE, a Mozilla-based JavaScript development environment, which was a precursor to NodeJS, BravoJS, which is a CommonJS Modules 2.0 extensible module system, and the CommonJS Modules /2.0-8 draft specification. Hamada is the AI task force lead at King's Distributed System. He supervises an elite team of developers that build cutting-edge tools for harnessing machine learning at scale. He's an experienced researcher turned developer in machine learning, and he has several publications and a host of exciting projects under his belt. He has previously been a TA in machine learning courses and neural network courses at Queen's University, where he graduated from. Thank you. So Wes, why don't we hand it over to you? If you have a screen to share, can you please let me know? And I'll go ahead and do that.
Fantastic. Yeah, I'm going to share my screen now. So good afternoon, ladies and gentlemen. My name is Wes Garland. As our host said, I'm the CTO of King's Distributed Systems, and I'm unable to share my screen because screen sharing is not allowed.
Is it because, could you tell me which browser you're using? Is it Firefox? So sometimes at Firefox and Edge has problems.
Let me see what I am using today, because I use them all. Today I'm loading Firefox.
Yeah, that would be a problem. Is it something that
you can
fire up in Chrome?
Sure, I can do that. And while I'm loading into Chrome, so you guys are going to maybe see two of me in just a minute, now I'm going to make my push about the free and open web and point out that it's really, really important to try and test and support all of our products on all of these platforms. Because once upon a time, we had a monoculture, I'm logging in, that was Internet Explorer 6 and Internet Explorer 6 and Internet Explorer 6 and Internet Explorer 6. And when that happened, the web essentially stagnated for a decade. We really need multiple vendors in the game at all times in order to keep this platform moving forward and benefiting our society. I'm going to close Firefox and I'll pop right up in Chrome.
Okay.
And here I am. Can you see?
Yes, we can hear you. Welcome back.
Thank you very much. Okay, so I am going to share my Firefox window because it's still loaded with the right slides. Okay, can you see the slides all right now? Okay, so my talk tonight is called Building a Future-Proof Distributed Computing Framework. This was kind of an interesting talk that I was asked to give. It's a little bit off the beaten path in terms of what I generally talk to people about, and actually I'm really excited about tonight's talk for that reason. So quite often I'm spending time teaching people how to write programs on the distributed computer, or I'm talking about scheduling algorithms and how the different components of the system fit together. But tonight we're actually going to talk about building this framework. This is what I've been doing with the last 2.5 or 3 years of my life, so it's kind of nice to recap a tiny slice of it, and I'm hoping to share some insight into the distributed computer, some developer life lessons learned, and then we'll get to the applied side a bit better with Hamada, who does really cool stuff. Okay, so the talk is called Building a Future-Proof Distributed Computing Framework. That's a very, very, very hard problem. And it was a problem that when I was hired at King's was so daunting that I almost didn't know what to do. Luckily, I have a couple of aces up my sleeve, and that is, how do we solve hard problems? We divide, split the problem into parts, and we conquer. We solve each of those parts. And if each of those parts is a very hard problem, we divide and conquer again. And I know this sounds like Computer Science 101, and it is, but it's actually a lesson that will, if any of you are at the beginning stages of a software development career, it is a lesson that will pay dividends for many, many years to come. So here's my About Me page. You heard most of my CV. The CV is not really that interesting, except to say that I've been developing for the web for almost as long as the web has existed. I've been writing software for almost as long as I've been able to walk. And I really love writing really good software. And a big part of my passion area for writing software, other than my intense interest in the JavaScript programming language, is writing really good tools to enable other developers to write really cool things, which is why I'm actually pleased that we have a task force full of guys here that does really cool things. I'm so happy to have Hamada and his team on board. So the original design goals when I came on board were essentially, let's build a parallel supercomputer capable of doing anything for millions of web browsers around the world and profit. There was kind of, I wish you could see me gesturing with my hands right now. There wasn't really kind of any in between those two things. So like I said, we started with a big ask, means we get a big problem description, and we have to narrow this down. So after many months of thinking and talking and listening to researchers and analyzing needs and capabilities, we decided to limit the problem scope. This is the basic step where you learn to walk before you run. So what we decided to build was a parallel supercomputer capable of solving perfectly parallel problems out of web technology. So you see, I've changed the problem statement a little bit. Perfectly parallel problems, when we talk about those in distributed computing, these are problems where the nth step of the problem does not require the results from any of the n minus z steps that came before it. So this is a very, we call these sometimes embarrassingly parallel problems as well. And these are essentially problems that can run apart from one another without any input between the different sections of the problem. And when you think of these at first as a software developer, it seems almost incredulous that we would need to solve these types of problems. But in fact, there are an awful lot of perfectly parallel problems, and that actually helps us on the business side, which is also really important in software development, figure out a market position for the product that we're building. So one of the things that we knew we couldn't do from the outset is replace everything. However, what we can start to do is make inroads in the industry by replacing or augmenting some of the lower hanging fruit. So we pick off, for example, the easy parallel problems with our technology and allow researchers to solve those problems. That means that the dedicated, very, very expensive, very, very limited hardware or limited availability hardware that is needed for performing some of the more complex types of parallel computing are now freed up and not doing these parallel problems. So by taking that workload from those machines, we actually enable more workload to be run overall. And that's actually an important part of why the company was founded. If you look at academic computing, in Canada, we have an organization called Compute Canada. And basically, I haven't worked in academia since the early 90s. But how it works is you ask for compute, And Compute Canada looks at your research project, and if you're one of the lucky 40%, says, okay, we're going to allocate you some compute, and then they're going to allocate you some amount that isn't the amount that you wanted, and that's kind of the end of it. We have a very large shortfall of computing in Canada, and that shortfall is getting bigger and bigger, and it's the same everywhere around the world. And especially as we're bringing on projects that need more and more and more compute exponentially as time goes on. For example, the square kilometer telescope array is going to be producing petabytes of data within a few years that is going to need immediate analysis, and we don't have compute capacity for that. Things like telescopes now, they're supercomputers, and we have to find capacity. Anyways, back to redefining my design goals. We call this V3 internally. V3 is actually what's running on the production network right now. We're getting very close to releasing V4. So when we designed V3, we limited the problem scope. We decided, okay, we're only going to really look at perfectly parallel problems. And rather than limiting ourselves to web browsers like the original vision was, we decided to expand our reach. We decided, rather than just looking at web browsers as places to both run these distributed applications, but also to perform the distributed computation, we decided to expand that, but without seriously restating the problem. So the expansion was to build our own components which can run that same code. That code is called JavaScript, in a secure way that we can get it deployed in many more environments than we could ever hope to get web browsers on. And that particular hope is really important, because one of the things we need in distributed computing is computers, and we need a predictable supply of computers, and we have to be able to forge these business relationships. So DCP is supposed to reuse unused bits of computer cycles all over the world. If you've got a second here, we want to use it. If you've got 10 minutes of time over here, we want to use it. If you've got a data center full of machines that's idle overnight, we want to use it. So we built this component that we can run on data centers and that we can run in screensavers on Windows machines to bring a supply of compute into our compute network. And then we also wanted to increase the likelihood of adoption of this technology. So another thing that we're doing is we're writing our distributed compute workloads in JavaScript, which is quite unusual for the industry. So if we're going to get people on board, not only do we have to write a really good API, but I have to be able to look people in the eye and tell them, hey, if you write a DCP program today, it's going to run in 10 years on whatever the distributed computer available on the internet to you is in 10 years, and we're going to keep it working for all time, just like we've done with all the other web technology since the roughly about 1998, I think, was the last major breaking change on the web for a standards track anything that has not been backwards compatible. So I'm taking a page out of the web playbook and also the CommonJS playbook. As you heard earlier, I was quite involved in CommonJS when that was formed. That's the committee that brought you Require, if you've ever done any JavaScript work. So I have to make this future-proof, which means good software design. And actually, quite frankly, that often means limiting what I specify so that I can make sure that everything that I specify is good. The big question on everybody's mind when I talk about the distributed computer is why JavaScript? Fundamentally speaking, I wouldn't be here if it wasn't JavaScript. Somebody else would have my job. My research interests have been very heavily into improving the JavaScript ecosystem now, almost exclusively since 2008, and I've been really interested in that since 2003. A key observation is that when you reinvent the wheel, you only get wheels. And what we really need is a distributed compute revolution, not just a stepwise evolution. A stepwise evolution is only going to get us so far. It'll get us bigger data centers, and it'll get us more expensive CPUs, and it'll get us more GPUs, and it'll get us more of this and more of that, but we'll have to buy all of them and provision them and pay for them and make Jeff Bezos, who owns AWS, very rich. So we're looking at JavaScript. JavaScript is actually very uniquely positioned within the industry. So JavaScript is trustworthy. Okay, you run untrusted JavaScript each and every day. In fact, you're running untrusted JavaScript right now to watch this presentation. If you're on YouTube, YouTube's front end is written in JavaScript. That source code is downloaded to your computer and compiled on it, and you're running it. We're reusing the same technology, and in fact, we're reusing the same implementation. We're standing on the shoulders of giants in terms of pulling these very good JavaScript engines and doing something with them. Remarkably, JavaScript is very fast. It's about 10 times faster than it was 10 years ago. This is because we have 4 huge companies spending billions and billions of dollars trying to make JavaScript the fastest thing on the planet. Our measurements actually show that it's only about twice as slow as C, which is really remarkable. So if you have a 10-core machine running CPU-bound C, and it finishes that workload in 10 minutes, you could finish that workload in 20 minutes on DCP with 10 cores. But if your workload is appropriately divisible and you spread it out over 1,000 cores, it'll be done in the blink of an eye. JavaScript is platform independent. And this is something that we've been struggling for years in the computing field, is trying to get a platform language that we can actually write code in once and run it anywhere. So we tried this with a number of things, X Windows and other things I can't remember, going back at the dawn of time. Most recently, we tried it with Java, and we never quite got there. But with the web, we've actually got there. So my wife can pick up her Chromebook, which is an ARM thin PC, and use this website. I can pick up my phone and use it. I can use it on my iPad. I can use it on my Windows box. I can use it on my Linux box, my Solaris box, running a Spark CPU, ARM CPU, x86, all of it. It all works. It's great. So this is, application developers are noticing this, and the web is the platform of the future. When you want to develop a GUI app for wide uptake today, the web is either your choice or was very strongly considered for it in almost every case. Something else that's really interesting about JavaScript is it's actually suitable as a compilation target. So you can compile other languages into JavaScript, which is not something that you're going to see with any other interpreted language. And part of the reason for that is that JavaScript has gone out of its way to define a subset of itself called WASM that allows that, and just the fact that it's so darn fast, it's actually useful. The only other language I know of that's been much used, high-level language that's been used as a compilation target, has been C. So we had the old C front, C++, and Fortran to C, F to C compilers back in the day. That's how those languages first came about. And we've actually done some of that work now, compiling these languages down to JavaScript. I'm just trying to keep an eye on my time and figure out how much I should be talking, which is not a whole lot more. Okay. So then we had to sit down and think, what do we want out of a distributed compute network? If we are running a perfectly parallel workload, we know that we're going to need a few things. We're going to need an input set. So this is the stuff that we want the computer to consider. And we need a work function, and that's how the computer considers the stuff. We actually don't need arguments, but I like arguments because developers tend to write functions once and then put arguments into those functions to make them do many different things with different input sets. And of course, a computer that doesn't give you any answers is no good. So we also need a result set. So we came up with the tiniest nugget that we possibly could to represent what our idea of a web technology distributed computer would look like. And that is an input set, a work function, arguments, and it needs to yield a result set. And of course, like I said earlier, we need to design good APIs if we're going to get workload onto this platform. They got to be good. And the other thing is they got to be good because I've committed to developers and I'm going to support them forever. So some principles that I use when I design APIs are that the APIs must clearly represent the problem in that problem space and leak as few implementation details as possible. Basically what this means is that developers should not need to worry about stuff that don't have anything to do with the problem that they're considering. For example, you should not need to worry about how to manage 1,000 remote instances of some platform if all you want to do is integrate a function. Similar APIs, they need to compose well, and this helps us actually build a framework over time so stuff fits together. So when I say compose well, I mean like Unix. So I'm a big Unix fan. I've been using Unix since the late 80s. I think it is the cat's meow. The great thing about Unix is that it has all these little tiny tools, and each of those tools only does one thing, and it does that one thing really, really well. And all of those things, they fit together in very well regular ways. Generally speaking, in Unix with the shell stuff that I'm thinking of right now, it fits together via standard in, standard out pipes. So every application emits its output out, standard out, one line at a time, and every application reads its input from standard in, one line at a time. So APIs need to feel right to developers too. This has something to do with clearly representing the problem, but there's kind of like I know it when I see it kind of feeling to API design. That it really is important in making things attractive to developers. One of the biggest regrets I have in life, okay, maybe not biggest regrets in life, but one of my biggest regrets in business is, maybe in life, I don't know, is that NodeJS implemented their version of the CommonJS module system wrong. And what they implemented wrong was allowing developers to return an exports object. I won't bore you with the details about why that's wrong, but I'll tell you why they did it. They did it because it feels right and it feels natural. And I can't fault them for that. Unfortunately, it had some very foreseeable knock-on effects, which is why the committee didn't spec that, even though it really did feel right. And another and a feel wrong example that I like to talk about is foreign function interfaces. So at one point in GPSEE, I reflected all of the single Unix specification v3 into script via FFI. FFI is like how high-level languages talk to low-level libraries. And we have arbitrary libraries for doing that in Mozilla's JavaScript called JSC types. We have that in Python called Python C types, and it's in lots of other languages too. I think Julia has it. Every language almost does this wrong. And what they do wrong is they make it so that the developer using C types has to know really arcane details about how the compilers and the CPUs on the machine where the program is running operates. So they have to know how structures in memory are laid out, whether the structures are packed, whether things are word aligned, whether they're double word aligned, whether the machine is big endian, whether, so that's the byte, the big one comes at the left-hand side or the right-hand side, what the word side on the machine is, and all of these things. These are all things that Python developers and Julia developers and JavaScript developers, they don't care about. They don't even know about it. And in fact, their programs are supposed to run on any kind of machine. It's supposed to be platform independent. Why are we putting these platform really hardcore bad details in front of them? And not only are they bad, if you use them wrong, the program crashes horribly and or has security problems. So that's why these are serious feel wrong examples. And I know why the framework developers do these, is because it's easy. I solved this problem for GPSEE, and it was not only a very difficult problem, I had to entrain a C compiler into GPSEE so that I could, in the background, compile structures and examine what the compiler was doing them under the hood so that the developers didn't need to know these details. Understandable APIs. So I'm going to talk about what I think is actually one of the most beautiful APIs ever written, and that is the C language for loop. So this basic loop construct has been borrowed in JavaScript, in Java, a few other languages, C++, and probably C#. I don't know C#. Anyways, Brian Kernighan or one of those guys coined it about 1970, and I find it to be a very beautiful construct. And the reason I like it is because it really expresses the problem that the developer is wrestling with very clearly. So we know that every loop has four basic characteristics. Initialization, a loop invariant, so this is something that is true throughout the duration of the loop, a propulsion step, which gets you from one step of the loop to the other, and the loop body code. And that's the code that gets run for every iteration of the loop. If you look at the C language version of the for statement, we can actually see all four of those things as clear as day. We see our initialization step down here. So this is the loop that goes from 0 to 9. What's true throughout is we start the loop by setting I to 0. What is true for the entire loop is that I is always less than 10 when you're in the loop body code. And to get from one step to another, we increment I. And we can actually look at the initialization, loop invariant, and propulsion step and prove to ourselves very easily that this loop will terminate. And we know that the invariant is going to be true for the entire body of the loop body code. So we can also reason about that code in terms of that loop invariant. So I realize this is kind of like a really dry CSE thing. But I hope that some of you can see the inherent beauty that I see here, where they've actually managed to take they've distilled the actual very essence of a loop into manageable syntax for developers. And that's what I love about it. As we were interviewing people trying to figure out what they needed out of a distributed computer, it became pretty obvious pretty quickly that loops are fundamental. We have, I think, D4 in Matlab, and we have another distributed 4 in R, and everybody's got something like that. And we use loops in distributed computing computing in general for everything. Numerical integration. We might loop over all the frames in a video or things to look at with machine learning. We might do parameter searches, et cetera, et cetera. So really, a loop is how we express this iteration concept that's fundamental to perfectly parallel problems. Remember, I said that I really limited my scope so that I could actually solve a problem, get to market, and then figure out how to get more money and more people and solve more interesting problems. So we had to build an API. Well, the first API that I built for the distributed computer is actually called, I won't reveal it yet, but we built it around the idea of this for loop. So I just rewrote this loop here on one line because it's more typical as to how you're going to see it in your program. And I started refactoring this. So I can't rewrite to JavaScript. I have to implement a library that works with it. So that means I have to work within JavaScript's existing syntax, and I decided to make a global called compute and give it a for method. And then I took, if you see these, I'm switching back and forth here, those three pieces of that loop statement, and I just made them arguments to compute.for. And then what do I do with my loop body now? This is syntactically incorrect JavaScript. No problem. I will make the third thing a function literal. JavaScript is functional, and as such, it has first-class function objects. And part of what I talked about getting the feel right, technically speaking, DCP doesn't actually use that function as a function. It actually looks at that function and immediately asks the interpreter to call it, to turn it into a string. And it's never used as a function in your program, even though I let you write it as a function. And the reason for that is because that feels right to developers. Plus, it gets your editor to help you with your syntax highlighting and so on and so forth, whereas otherwise we'd have to get all of the editor authors to come on board with a DCP mode so that people could program in DCP without making really trivial errors because of bad syntax highlighting. So these are fundamental things when we're trying to come up with a platform that really do matter. And then, of course, so I started here, and I've got my syntax for what compute.for looks like, but that's not a complete program. So I have to talk about some other fundamental concepts in distributed computing, like a job. We use jobs in batch processing, and perfectly parallel things are not really that different. So I made the return value of compute.for with all of these arguments be called a job handle. And then I gave the job handle an exec method. And that exec method actually runs off to the scheduler, and it sends all the pieces of the job up, and it sends the code up. And then the scheduler sends all of the pieces of that out to the workers. The workers answer back with their answers. The scheduler takes them, sends them back to my program, and that return and the exec function finishes the await statement there, and you've actually got your answer back. So what I've got here is something that actually does do distributed computing in a very manageable syntax for developers. And because of this, I think I will actually manage to have better commercial uptake than if I presented them with a whole host of RESTful APIs that they had to submit queries to in order to actually have work done on the network. Or worse yet, gave them some kind of crazy configuration console where they have to turn around and declare a whole bunch of zones or containers and then applications to run in those zones and then compile them for the right architecture and all this other stuff like we have with some of our competitors. So we've limited our problem. We've limited our capabilities, but what we've done is a really good job of that capability so that hopefully we can use this as a nugget to explode out into becoming a successful platform and a successful product, and really do some real work on the network. And to that end, we're actually starting to have some really good uptake. We have about 1,000 cores on our network right now that are ready for anybody in this room who wants to do some work on them. So of course, to have a complete program, we also need to do something with our stuff. So what I added here was a little event handler that says, okay, well, when that loop code does a console message, I should have been console.log, I made a typo there, that the job should receive those console events and do something useful with them on the local console. So this program here, if I didn't have that little syntax error in it, would cause hello world to appear on my screen 10 times by the time that job.exec await statement finished. So yes, we added a console API. It's exactly the API on the worker end that you think it is if you've done JavaScript work, because it has to feel right. So now is kind of the time where I say, who wants to try this out? And that's going to mostly be the end of my talk. And then I am going to turn over the floor to Hamada. So for the let's try it out portion, I am going to ask the moderator to put my face back on the screen. Know when I'm there. Oh, actually, don't do that. Leave my browser up if you could, please. Sorry. I'm going to load an application here. Now, this application is, we call it EMCoil internally, and this looks like an academic paper that is not rendering properly on my screen for some reason. Anyway, it's called Electromagnetic Forces in a Something Coaxial Bobbin Coil and Tube System. And as we scroll through this document, you can see that it looks very much like an academic paper. So one of the things that we've also been wondering down at DCP is, what are we going to be using the distributed computer for? And more interestingly, in some ways, what will academic papers look like in the future is one thing that we've been wondering about. We wonder about lots of things down here. We have a lot of good times. Yep. Does somebody need to jump in there?
No, go on.
Okay. So you can see that these equations here are, if you know this kind of math, and this is not my forte, they take a lot of compute to solve. Dan Desjardins, who is user 0 on DCP, is also the CEO at King's Distributed Systems. This is his actual novel research, and he used to burn out laptops at computer labs with little slices of his problems running in, a couple dozen different instances of Maple or Matlab, just trying to get the answers out for his physics research. And what we've got here is a paper where, wow, this is not rendering properly. I'm just going to switch my shared, actually I'm going to try reloading first. I'm going to switch my shared screen because a piece of the paper's not loading and I need to type into it. There we go. Okay, that loaded properly this time. I wonder what's going on there. So I can change a few values here. And the idea behind this is, why don't you let people who are reading your paper also change some values and rerun your math. And so we wind up publishing interactive Scholastic papers. And so what I've done here is I've said, okay, I'd like to see the math with these numbers, and I'm going to hit compute right in this paper. And I'm going to get the answers right in this paper. And you notice I haven't downloaded anything. I haven't installed Matlab. I haven't spent days writing equations into math modeling software or anything like that. I'm going to have to do one thing, though. I'm going to ask everybody on this call to help me out. And to help me out, you need to visit a website called dcp.mn. That's Delta Charlie Papa Mike November. And when you visit that website, you'll see a DCP worker. And what we're forming together is a private compute cluster. And when you hit start on that, you're joining that private compute cluster. And there's a scheduler running in the back end that is an early version of our V3 product that puts the compute together with the supply and actually performs these computations on your computers in JavaScript. And you can see the progress bar down at the bottom moving there. You can probably see the progress bars on your own machines working. And so together, we're actually teaming up to take our unused idle compute power, and we're doing actual scientific research with it. So this is why some of this stuff is so exciting. It has real world applications that are very immediate for me. Hamada is going to talk about some more of those. So if we could cut over to Hamada, please.
For sure. I'm going to go ahead and start sharing my screen here. Perfect. Thank you so much, Wes, for that intro and lovely talk. Hello, everyone. I'm Hamada. Mohammed Hamada Gazmala. I'm going to be talking about distributed compute, data science, data engineering, and machine learning in general. If you ever hear me say anything about DCP, that just stands for the Distributed Compute Protocol. So you can basically just do a mind switch there and it'll all be good. I'm going to talk a little bit about me real quick. So I'm a Queen's University Masters of Computer Science alum. Started off actually doing game design, doing AI specifically in game design. And I realized that there was this big thing happening in, 2014. It was more like 2012 is when it started booming really big, this AI boom. And I realized a lot of the stuff that was happening in machine learning and neural networks could actually be applied for game design. And that's when I hopped into computer vision and started focusing a little bit more on computer vision, neural networks, and motion smoothing and that sort of thing. This, of course, takes a lot of compute. Here are a few small projects I've done in my day. On the left there is a reinforcement learning, multiple models, time delay, Q learning solution, which essentially does some interesting stuff with the Q values in such a way as to allow for a time delay to action reward value pairings, which is really interesting. And on the right there is my master's thesis. Some video there on motion smoothing of video-based object detection for analytics and systems intelligence purposes. So those are the sort of work that I started off doing in machine learning and AI, and I sort of moved on from there when I, got a job at King's Distributed, and I am now the lead at the AI task force, and our job is to sort of take what Wes has built, this amazing tool that allows you to distribute huge amounts of work in JavaScript and allow folks who are doing machine learning and AI problems to solve them using that tool. Now, the majority of people typically use Python or other languages to typically challenge those problems. And so we wanted to be able to make the stack smooth so that when people are transitioning to using DCP, they have either, almost zero code in some cases in Python to change with one or two lines to add on, or in certain cases, a smooth transition into using typical API calls that they would be used to, so that they can distribute out their TensorFlow jobs or their SciPy jobs or their NumPy jobs, for example. This is really interesting to me because this is the first time that we sort of easily allow a broad variety of users to be able to distribute a large amount of slices of work to huge numbers of compute nodes without having to worry about orchestration of those nodes. So that means no requirements, no manipulating of containers, no changing of any of that. You don't have to worry about that at all. It's all managed by our scheduler. And so that means that a large number of people can actually get started right now and sort of write whatever code they want to solve whatever problem that they want to solve. And you might be interested, what exactly is happening with the distributed, like what is the distributed computer? Everything that's Wes talked about should have answered that, but I'm going to talk a little bit more about why you would want to use it for machine learning. What could you possibly benefit from learning to distribute your models or train over multiple compute nodes that you might not be able to do with a single really expensive computer? Well, there's a few examples, canonical examples of this. We can take a look at the transformer architecture, for example. This table from a paper in 2019 called The Evolved Transformer used the transformer architecture they did a neural architecture search, on the transformer architecture, so that they could try and extract the right set of hyperparameters to get essentially the best model perplexity. In that specific paper, they trained 5,000 models in order to be able to find the best model. The transformer architecture is not exactly the lowest computational complexity model to train. It is quite complex and requires a lot of compute. In fact, hyperparameter searches, extremely large models, huge ensemble models, multiple experts, and so much more in ML can all be aided by using some sort of distributed compute if it is available and viable for the actual researcher or corporate to be able to do. Now, when I was in research, we didn't have access to, thousands of compute cores. But if I had access to thousands of compute cores, I can only imagine what I would have done with my research. And that's sort of one of the reasons to do distributed machine learning. But I'm going to, nail this nail on the head and give just another example to really, accentuate what I mean when I talk about distributed machine learning. So you may have heard of Google DeepMind's AlphaStar. The paper, I think, is called Google DeepMind's AlphaStar, Grandmaster Level in StarCraft 2, which used multi-agent RL in order to be able to train a whole bunch of agents, 33 or so agents, to play StarCraft at a really high level. This is a really, really interesting paper, and it's really amazing what they were able to do with it. But to be able to do this paper, it was only possible because Google DeepMind, being Google, had access to 33 third-gen TPUs for 44 days. That 900 or so agents were trained to play StarCraft 2, but only 33 of them were selected out of those 900. And then they were trained in RL games against each other for another 27. This network could not have been possible. This would not have been feasible on a single computer. Not in a decent amount of time anyways. In fact, let's quickly talk about how much that would cost for you. If you wanted to rent out a TPU right now, a third generation TPU, it would cost you this much according to Google's website. Now recall that AlphaStar 2 was only possible using 33 third gen TPUs for 44 or so days, plus another 71 days for a total of, I believe, 56 232 TPU hours. For $32 an hour, you're looking at $1.8 million of compute. Now, unfortunately, Google doesn't actually sell TPUs. Otherwise, I would just tell you to go buy, 33 TPUs on your own, and you might be able to, make it work. But since they don't do that, they have a special pricing for, if you want to rent it out for the whole year, you'll have to call them up, and I'm sure that'll be pretty expensive. And if you're doing research and you want to try to, recreate this or reproduce this paper or make it a little bit better or whatever, you'd have to pony up or try to convince your PI somehow or an accountant that you really need, that $1.8 million of compute in order to recreate AlphaStar 2. Thankfully, that's sort of where DCP comes in, the distributed computer comes in. We're trying to make distributed compute not only easier to use, but cheaper for researchers or industry members. I'm going to do a quick demo. I'm assuming that most people here have, since this is, data science and data engineering series, some experience with SciFAR and with convolutional neural networks. But just a quick overview, SciFAR is a classification data set. where there are a series of images that are classified to one of 10 classes, and a convolutional neural network is a specific type of neural network that performs a convolution, which is a signals processing function, over the input image with a set of kernels that are learned using backpropagation. I'm going to very quickly touch on that. So this is this demo that I'm going to be presenting is a very small example wherein you're a user who has just trained some sort of app. Your app classifies specific images, whatever they may be, and you want to be able to host this model of yours somewhere, and be able to handle a large number of people who one day end up using your app. In order to be able to scale well, you might have to, in the canonical sense or in the typical case, you might, go ahead, sign up for AWS, pay them a bunch of money to use their Elastic compute. And then one day when you wake up in the morning and your app has gotten super popular, you have to pay them quite a lot of money as they had to, expand quite a lot in order to be able to accommodate for the number of people that you suddenly have using your app. Now, if you were using the distributed computer, you wouldn't have to do that. So you wouldn't have to orchestrate all this Elastic compute stuff. You wouldn't have to worry about making sure AWS has a set number of prices or a price ceiling that you'll hit, so that et cetera, et cetera. You can take advantage of compute groups and heterogeneous hardware in order to be able to make your own compute group that can scale out to large numbers of inferences on your specific app. So I'm going to go ahead and go to this link, and I'm going to, if you want to use the specific Colab, feel free to pause this and go to that link, but I'm going to go ahead and switch to this Colab, and I'm going to go ahead and ask people to be patient with me as I go through this very small demo here. So in this demo, we're essentially using Google Colab to be able to launch a distributed computer job, which is pretty funny, if you ask me. But we're going to do some initial environment initialization. So this is just setting up all the stuff that we need in order to be able to use DCP with the specific ML stuff that we're going to be using. Now, since most data scientists are comfortable with machine learning in Jupyter Notebooks, I've decided to make it a Jupyter Notebook as it's nice and easy and comfortable for folks to use and modify as they need. So this is going to go ahead and load in, oh, it looks like it's MNIST. It was supposed to be Sci-Fi. Don't worry about that. Some data set here, and we're going to do our pre-processing of it. We're going to build a variational autoencoder for that, and we're going to go ahead and train our variational autoencoder on that. Now we have this trained model, and I'm going to, write up some app on Android or iOS and publish it out. That does something interesting where it generates some sort of numerical digits between 0 and 9, and we want that numerical digit to be something that's never before been seen. We want it to be representative of the internal distribution of the data of MNIST, and we want to do it in such a way that we're taking advantage of DCP for our distributed inferencing. So we're going to go ahead and publish this model. So we're going to quantize it here. So make it a little bit smaller, make the weights uint8s instead of float 32 so that we can save a bit on space there. And then we're going to upload our keys. Now, keys are important for DCP. Wes may not have mentioned it, but they're a way of essentially authenticating who you are and what bank account you'd like to pull your credits from. And then we're going to go ahead and publish this model. We're going to set a few little parameters here, which scheduler we're going to use, the number of images per worker we want to generate, the number of workers we want. And you'll see here, oh, it looks like I've already completed it. I distributed out slices earlier to be able to, ahead of time, get some nice results. But this is the compute.for that Wes was talking about earlier. So essentially, we're just going to be sending out, how many we want to compute, the batch size for each of those to compute, and the function that we want to compute. So this function just loads our TensorFlow.js model and feeds it some sort of normal distribution of noise, and it generates an output image for which we return back to the client. And at this point, we have all of our results. We make it into a NumPy array of size, batch size times number of computes by 28 by 28 by 1. And now we can actually go ahead and run this. We can actually look at the samples that were generated on 100 different workers, each worker generating 32 different samples. And that's the 3200 by 28 by 28 by 1 there. So this is a pretty simple case, pretty trivial case, I would say, of an example of using DCP for distributed inferencing in the case that you might have some sort of application that you'd like to easily distribute out on DCP. So that's the small demo, so that you have in mind what we're sort of capable of right now. But I'd like to go ahead and talk a little bit more about sort of the future of where this can go and what I envision, distributed inferencing or distributed training to look like, and the sorts of things that we can do. And in particular, I want to focus on distributed training. So typically when we talk about distributed training with deep learning models, we talk about two methods. We can either, let's see if I can, there we go. We can either talk about a sort of distributed model. So in this case, we take one model that we sort of split up, and each part is on a different machine. Each weights are on a different machine. Or we can talk about distributed data. So in this case, we have each machine has one model, and they are training on either different sets of data or the entire data sets or whatever it might be. But what's important is that the full model is on each machine, and thus the only thing it has to communicate with the parameter server, which stores the weights for the neural network, is either the gradient updates, the Jacobians, or whatever specific way you're trying to update your parameter server. And it's quite clear that of these two, model parallelism, where you're taking your model and splitting it up in different machines, has a lot of internode communication. And Wes was saying earlier that he was focused on this very small subset of embarrassingly parallel work. And currently, huge numbers of each one of these bold lines here is model intercommunication. You can see that a lot of them are communicating with one another. However, this one here, this parameter server with machines communicating only their gradient updates, this is an interesting case where there's fewer in terms of per inference internode communications, but we do have to every once in a while send back our parameters, our gradients, whatever, back to the parameter server. Now, there are some interesting properties that emerge where other machines using these updated parameters can learn from data points that were not generated by that machine. So for example, if machine one has some data about cats, and it learns the right set of gradients that would push its parameters into an optimal space for detecting cats, it might send that off to the parameter server. The parameter server would update, and machine 3 here, which has never in its life seen a cat, might actually get some of those gradients flowing, and its parameters would actually know to be able to recognize some of the features of a cat, and would be able to have learned essentially from the data that machine 1 had actually seen. Now, the simplest case to see for this is actually text correction, or at least the simplest example of federated learning anyways, is often the text examples. And this sort of methodology where different machines are learning on different data or decentralized data in a distributed collaborative training of a predictive model is typically called federated learning. So in this case, we have this phone A, which is generating data as the user types in their text and, maybe autocorrects or whatever it might be, is generating data that is used to train their internal model. And those gradients at some point get sent out to the cloud where they update the parameter server for all of these models. And, that parameter server pushes those parameters at some point to all of the phones that may need their update. Google actually does this a lot with a lot of their Android technology. This is like real tech that they use. They often allow users to actually have personalized models that slightly deviate from the collaborative model. So I assume that there's a set of data or a set of gradients that they're keeping track of for the specific user that they always apply and can remove from the set of parameters that are used in the specific user's data. And this is really interesting because that means if someone else has some problems with specific text that they're typing, all of the phones end up learning from that specific person's mistakes and that specific person's data. Now, naturally, as we're starting to talk about communicating gradients and possibly gradients coming from data that might be sensitive, in particular, bank information or passwords or whatever it might be, it's important that we are able to make sure that we're taking into consideration privacy. As we all know, data is gold, and privacy is extremely important. So the typical use case for some sort of federated learning would be encrypted communication of the gradients as they're passed through, and some sort of form of immediate averaging with all of the other updates so that we sort of lose track of where it came from and obfuscate away all of the updates. Now, this is especially important considering recent advancements in AI, where researchers have actually been able to reconstruct training data using information on activations before an update and prior to an update. So that is, if you were to take a model and you predict on it some set of activations and you record those, and then you update the model with a new set of data, and then you again predict on some sort of set of activations, then you can actually take the difference in the activations and train a network to be able to reconstruct the actual updates of that model. Now that's really interesting here. In this case, the middle one here is, I believe, the first row is the original samples, the second row is the reconstructed samples based off the updates, and the third is the reconstructed samples off the autoencoder, which is supposedly the upper bound of the reconstruction attack. So federated learning has this principal format that we need to talk about. So prior, we sort of talked about all of the phones sort of giving out that update. Now, it's not necessary that all of the phones participate in the update. And in fact, typically we assume that there's some sort of selection phase. So we select K number of devices to participate in the current round of training. And these devices will be sent the latest set of dates, latest set of checkpointed weights, as well as configuration for that training. So like learning rates, specific optimizer, hyperparameters, etc., etc. Once, and as well as data, or they will use their own data. Once they get that data, they begin to train. And once they're done training on their own local data or data that they've been sent, they will submit their parameters or gradients back to the cloud server. So that's the aggregation step here. Now, of course, because this is the real world and we all have phones that may not always connect, you might be connected when you're, let me go ahead. You might be connected when you're selected for participation in training, and then disconnected when you're done training and thus cannot send back your data. We assume that if a device takes too long to return, that it's basically lost, and thus we ignore it. If we received model weights, however, we average them in the federated averaging scenario, though sometimes we'll just collect them all and apply them all at once. Then we just apply them to the model weights and checkpoint that model and go back to selection for round 2. In the online federated learning case, we do this until we're satisfied with our results, or forever, and lower the learning rate as we go. Basically, until we find a system that's either reaches some sort of equilibrium or reaches our desired behavior. Now, there's many different variations of federated learning, a whole bunch of different ways people can use it, using either supervised or unsupervised data, even sometimes using like reinforcement learning concepts in order to be able to do that. A good paper on that is When Deep Learning Meets Federated Learning. I recommend that. And I expect there are many more to continue appearing as we start to as more and more data scientists and data engineers and machine learning scientists consider distributed and parallel compute as one of the primary, if not necessary, ways of training large and unwieldy models, as well as to leverage user data in a way that's safe and private, and in such a way that whoever owns the data, such as the hospitals in this case here, can actually keep that data private, but aid other hospitals in some new global heuristic medical model. And all of these different variations may need to run on different hardware. So you might want to be able to run your federated learning model on, ARM processors inside of drones, or maybe you want to run it on old and deprecated MRI machines at the hospital, or maybe you want to be able to run locally at home using a whole bunch of, smart fridges, smart vacuums, and of course your desktop rig. And that's where DCP excels. Essentially being able to allow arbitrary functions to execute in heterogeneous hardware by leveraging, JavaScript and the underlying stack. Additionally, the concept of compute groups, as Wes was talking about, really aids in being able to form these sort of privacy-enriching compute groups where you know that your data is only being sent to people who are in the compute group, and thus you know that they have access to that data. And the future of DCP and federated learning is extremely bright, and I have a lot of hope for it, and I believe that it's extremely extensible, and I can't wait to see what we have in store. That's everything for me. Thank you, everyone, for this opportunity. And are we moving on to questions?
Yes, thank you. That was great. It was pretty incredible seeing not just the demo, but everything that could be done around federated learning and the distributed data sets and the distributed computing platform that you have, DCP. So yes, it's time for some questions. So we have quite a few people watching live right now. In case you have any questions, please feel free to type them in the YouTube chat window, and I will read them out as they come in. But to begin with, I have a few questions of my own, if you could start off with that. So what are the languages and frameworks that could be used right now with the distributed computer? Could we program in Python or integrate with a package like Matlab?
I'll go ahead with this one, Wes, if that's okay. So the DCP's main stack is JavaScript. So we expect everything that executes inside of a worker to execute in the JavaScript runtime. However, we do have some ways of allowing folks to run a small subset of Python, essentially. We do this using emscripten, which compiles certain C projects into WebAssembly, and thus allows it to be run in JavaScript. And thankfully, Mozilla had a project called Pyodide, which allowed a small subset of the data science packages such as NumPy, SciPy, scikit-learn, pandas to be run on JavaScript. So short answer is currently Python and JavaScript are Python is experimentally supported. JavaScript is fully supported, and I hope to see in the future any emscriptenable language runtime to be runnable inside of the JavaScript workers.
Hamada, are you aware of the Matlab work that's been going on?
Yeah, Matlab. I'm only aware insofar as there is a Matlab tool that allows you to export WebAssembly from Matlab, which would allow using those exported functions or exported scripts in DCP. But I'm not aware of how experimental it is right now.
My understanding, for what it's worth, is that it's really, really, really experimental, but something has worked. So we're actually looking at getting Matlab up and running on the distributed computer at some point. Really, the question there is not if, but when.
Hey, I think we'll all take that, even if it's running right now in a primitive state. I think we'll all take that. all wins as we go along. Yeah. It's interesting you brought WebAssembly, because that was one of the questions that I had. I know JavaScript can be pretty restrictive in what you can do, what you can run on computers. Obviously, it doesn't have access to a number of resources which are present on the computer. There's significant limitations, and by design, JavaScript is designed to be restricted and doesn't have access to a number of resources. So that was going to be another question. How do you ensure that the appropriate resources are available in order to do what you are supposed to be doing? For example, we talked about you explained that already, that through WebAssembly you can do things that traditionally you could not do with JavaScript. But what about how to get control over where the job executes or how it executes? Can we get the job to execute on CPU versus GPU? Is there some kind of insights like system monitoring insights that could be obtained through all of that?
And I'll take the first half, and Hamada, I'll get you to follow up with the second half.
For sure.
That's a really interesting question, and actually, it's the exact opposite question than what I normally get. Because of the people that I tend to deal with, 99% of the time, their question is, how do you make sure that nothing is doing stuff that it's not supposed to? Your question is how do I make sure that I actually have the resources that I need? And interestingly, they're actually the same answer, more or less. Part of it comes down to the idea of limiting the problem, which I talked about earlier in my initial design. This is definitely something that we have to do in a framework like this when we're starting out. We have to walk before we run. JavaScript is actually pretty unique in the world in that it is a very capable, very fast target for running instructions, and it's very safe. Okay, one of the things that's safe about it is JavaScript doesn't have the concept of I/O. It doesn't have the concept of uninitialized memory. So when you don't have the concepts of these things, you don't have to worry about securing them because they simply don't exist. That's, of course, that is great from a security point of view, but it's terrible from a functionality point of view because a program that can't interact with the world is not a useful program. So what we did when we took the core JavaScript engine that can't do any of these things, we grafted a few things on it that we needed that we could use to bootstrap the remaining functionality. So in particular, the V8 engine, which is like the pure JavaScript engine from Google. It does arrays and functions and objects and addition and subtraction and mathematics, and that's about it. We added into it the ability to read and write from a socket. And then we also added the ability to nominate a function to be called after a timer expires, to set the expiry time of said timer, and to quit the program. That's the only 5 things that we added to our basic, what we call our evaluator, that is built on top of JavaScript. So that helps me understand that I have a good security envelope because it's almost impossible, in my opinion, to take a large capable thing and to plug all the holes for every version that hasn't been written yet and call that a secure product that I would be willing to share my banking information with. However, if you take a product that has no capabilities and then you add a few little ones, you only have to make sure that you've added a few little ones correctly and securely, and then you don't have to worry about developing leaks when you're not looking because somebody's added something into the language over time. So if we take a look, if anybody here on the line is an experienced web developer, they'll say, yes, but what about XHR and fetch and all of these things? They're not JavaScript. That is part of the browser's environment, that the browser provides this environment that the JavaScript code runs in. But that's not part of JavaScript. We don't have that. So we do all of that stuff over a socket that goes back to what we call our supervisor. And this supervisor never runs workload. It's just a Node.js program that talks over the network, and it talks to our evaluator, and it gives it workload, and it takes responses from it. It feeds it modules, it gets answers, and that's about it. So that's how we get some of that stuff. So if we need to add functionality into the evaluator, what we do is we actually wrap it up in the supervisor, then the supervisor serializes it to a string, shoots that string over a socket, and these aren't even promiscuously shared data structure sockets. They're actual real TCP sockets. There's no instructions going over that. And WebAssembly, by the way, never compiles to machine code. It only compiles to essentially JavaScript tokens. So you still have the JavaScript virtual machine running those things. And that's how all those functions are added, except for two really important exceptions. Actually, only one, and that is Web GPU. We've taken the Web GPU product and we have taken Google's version of that and grafted it onto our evaluator. This is still an alpha, but it's working well. And Hamada can actually talk about what capabilities that unlocks.
Yeah, for sure. Web GPU enables us to essentially be able to write GPU, so general purpose graphics programming, shaders to do convolutions, matmuls, all the lovely stuff that we love doing in machine learning and AI. And that means that TensorFlow.js, for example, can take advantage of your V100, your A1000, your RTX A6000, your 3090, whatever it might be, and take advantage of all of them on every compute node if they happen to have one. That's something that's, of course, users are able to request capabilities for, so they can ask the scheduler that their job be put on a machine that has access to Web GPU enabled capabilities, and thus are able to leverage those specific abilities.
Oh, that's very interesting. I didn't know that. I didn't know that was a thing. Thank you for explaining that.
Yeah,
And
we're actually one of the first to natively implement Web GPU at all. So it's
not one of the
first to natively implement Web GPU like that. So that's something we're pretty proud of.
yeah, that's always a nice place to be. You know, be only the sole company that has done something incredible like that. That's always a nice feeling to be in, a nice place to be. So just to be conscious of time, you know, I have one last question before we can conclude. So how does this fit in with computing services like EC2 or Lambda, storage services, and other orchestration tools? Could it be used in conjunction with all of these? Have you compared and contrasted it with, for example, something like MapReduce?
Hamada, that's your question.
For sure. Yeah, I think that's a really good question. I think that's a really important question. Our service is a little bit different from all of those in many different little ways. So whereas in some of those you might have to specifically set up the environments to work with specific, set up CUDA 1,000 times on 1,000 different machines, or write scripts to do that for you, to make sure that you have all of the ports set up right. Or write, containers to do all that for you and deploy those all out. Unlike all of that, our service doesn't need any of that. It's an orchestrationless solution. All you have to do and all you spend time focusing on is writing your work function and making sure that your work function does what it needs to do. And making sure, of course, that you have all the capabilities set right so that we can actually give you a computer that does what you need it to do, or a node that does what you need it to do. And that means that unlike all of those other solutions you mentioned, we don't need to worry about, you don't need to, the user writing it doesn't need to worry about requirements, modules, packages, et cetera, et cetera, et cetera. We all do that for them. Now, of course, if one wanted to, one could launch up a few EC nodes, Elastic Compute nodes, and run workers on them. And you could, provide compute through those compute nodes, or maybe even burst onto them if you find that the compute nodes currently provided by the production scheduler aren't enough to meet your specific compute needs. And if you wanted to do that, we are, pushing with AWS and working to try to get some good functionality, so that's some good UX, so you don't have to worry too much about orchestrating that either, so that it's all done for you behind the scenes. That's sort of where we fit in with the compute marketplace, I guess.
Okay. And have you taken a look at recent projects like Folding at Home? Well, Folding at Home is not a recent project, but it has been around for some time. But are you familiar with, for example, Folding at Home, which tries to solve the problem of protein folding in a distributed computer?
Mm.
So the idea is that you download something and run it on your system, and collectively through these distributed computers, hopefully that will solve the problem using the collective CPU. But my guess is these projects require a software to be downloaded and installed, whereas in your case, there is no download and there is no install because everything is running within a browser in a JavaScript environment. Is that correct?
That's a big part of it. Folding at Home, Hamada, do you know, is that a Boink project?
I believe that's Boink, yeah.
I think it is. So there's Boink has a few, in some ways it's very similar to what we're doing. So they're taking small pieces of a project or of a problem, and they're distributing them out throughout the world. They're getting the answers back, and they're putting it all back together again. What's really different from ours is who can run the code, what code can run, and what has to be done to run the code. So the code that runs on the Boink network, if I understand correctly now, don't take this as gospel, because it's not my, I haven't looked at Boink in 3 years now, and I haven't done a lot of work with it. It was just part of my initial study when we were trying to figure some of these things out. You have to compile the code. Okay, so that means that if you are a person running a Boink project, you have to first of all figure out how to put the stuff together, get the data in and out of the real application that you're trying to get the answer for. So we solve that for you. And then the next thing you have to do is you have to compile it for the machines that are going to be running it. So if your machines are going to be running ARM Little Endian, you got to have an ARM LE binary. If they're Big Endian ARM machines, you're going to have an ARM BE binary. You need an x86 binary. You need an AMD binary. Now that we got Apple out there with the new M1 processors, you got to have Apple M1 binaries. And it starts to get a little obnoxious.
Yeah.
But then the interesting thing is, now think about the people at home that are running Folding at Home. Now, Folding at Home is one application that runs on that entire network, so people are pretty comfortable with it because they trust the Folding at Home guy. DCP allows anybody to run stuff. You'd be crazy to allow somebody you don't know to run binary code on your machine.
Yeah.
Because that, that's instant. I doubt that network will survive 3 hours without a major security vulnerability wiping out the founder's bank accounts. So the fact that we handle that orchestration for you is really important. But what's also important is that because we have that kind of security envelope where we feel confident allowing anybody to run code on anybody's computer, that allows these little projects that come from nowhere to just suddenly exist on DCP. They don't need to make a whole SETI at home or Folding at Home or this or that or asteroids at home. They don't need to come up with these entire social movements in order to recruit workers. They just need to write the programs and give us $20. It's a completely different paradigm. And I'm actually really hoping that once we launch, bigger than we are now, we got lots of really interesting features coming up this year that should make us a lot more attractive than we are right now. My biggest hope is two things. One is that we attract some amazing product that does something amazing with us that I haven't thought about. And my really biggest hope is that somebody comes up with a new branch of computer science that is involved with using algorithms to solve problems on hundreds of thousands of cores, because nobody is doing that research right now. But I'm sure that if we put, a million cores in front of a bunch of researchers, they might come up with a really cool thing to do with it that you couldn't do 1/10 of with only 100,000 or, 1,000th of with only 1,000 cores. But we've really never put this kind of surface in front of researchers. So what really excites me is really there is, I believe, a possibility to be solving algorithms a completely new way with DCP inside of a decade.
Yeah, I can imagine something like that. I was saying something like the Human Genome Project, which was a remarkable achievement. Would that be the kind of projects that you are looking for?
Oh, that would be amazing. I mean, I remember when the first human genome was sequenced. That was a really big deal. That wasn't that long ago. Yeah.
And so I'm very curious. I know we are way over time, but this one, because it's such an interesting and fascinating area, I just can't stop. So I'm on the dcp.mn site right now, and I was running something, a task that was running. So I see some information that is present, a number of active tasks right now. There's nothing running. how many tasks were completed too. So that was when you were trying to do the demo. So that's when I moved and I ran something over there. But there are two, and there's an uptime field which presumably shows how long a task had been running. But there's one thing called credits earned. Could you tell me a little?
You've discovered the economic side of DCP.
Yeah.
So there's a couple of different things that are very interesting with DCP. Not only do we allow you to run compute and pay for it, but we also allow you to earn credits, which you can use to deploy more compute, and in the not distant future, you'll be able to turn them into money. And this is how we intend to attract supply to the network. We want people to donate their idle compute. This is your computer when it's normally it would be off at night. Just leave it on and run the worker, and get a check every month. Why not? And that's how we intend to bring some of this out. And there's whole new revenue models tied just to doing work. So, for example, there's a model that we call the New York Times model at the office. Part of our client library right now actually allows you to make your own workers, and they talk to our central scheduler and they can receive workload. So if I was the New York Times, I might decide that my paywall was not really serving the needs of my readers, and I might decide to get rid of the paywall, but I'm still going to need revenue, and ads just don't pay the bills on the internet like they did 15, 20 years ago. So what am I going to do? Well, maybe, just maybe, I'll put a little corner of my window, I'll put a DCP worker in there, and I'll use one of your CPUs while you're reading the New York Times to do work for the distributed computer. And I'll have configured that worker to send all the money to the New York Times bank account when the work is complete. That way people get to read the news, New York Times get paid, science gets done. It's win-win-win.
That's very fascinating. And that could be, again, a free model because New York Times right now is a subscription, right? You have to get a subscription in order to read that. So people who would be willing to let that compute being used would get New York Times for free. Wow, that's amazing. That's incredible. And
I'll add one more pie in the sky idea that I would really love to see. There are places in the world where not everybody can afford a smartphone. Wouldn't it be amazing if someday the DCP economy was enough that all you had to do is plug in your smartphone at night to pay for it?
Interesting. That's interesting.
So these are the kind of problems that we're really excited about potentially using this technology to solve. There's compute lying around everywhere. Why not let the people who own it monetize it? Why not let the people who need it buy it?
True. Very true. And they have control as well. So you mentioned the security envelope that has been provided as part of this platform, but they also have control. So I'm assuming that if they close the browser, the processing would end. It would stop at that time. There's nothing going to be running behind the scenes. Is that correct?
That is correct. And in fact, our model is geared around the idea that the computer owner could take away the compute from us at any time without any warning at all. And that's okay. And in fact, one of our primary products is a screensaver for Windows. So when you walk away, screensaver comes on, you do compute, you sit down, you hit a button, compute's gone. And we do our very best to make it completely invisible because we know that if we annoy you, you'll uninstall it. And so the scheduler handles that. The worker goes away. We have a daemon that detects that. The work gets rerouted someplace else. If it's running late, we do it someplace here. If we need low latency work done, we send it out to multiple nodes, and then whichever node comes back first, we take their result. That kind of thing. So there's lots of there's lots of different ways we can solve those problems. And in fact, that even allows us to use on-demand compute from our competitors if we wanted to back our compute. Because they do the exact same thing. They take away compute from the lowest price tier without any significant notice, and that doesn't bother us in the least. We're designed around the idea that that's going to happen anyway.
Okay, that's interesting. This has been fascinating. It's been an amazing conversation. I know we're way over time, but the questions, this is such an amazing and incredible area. So we have a number of individuals who come from academia as well as industry, researchers and practitioners. So if they are interested in working with you on potential projects, research projects where they feel your distributed computer could be advantageous, they could reach out to you on LinkedIn. The LinkedIn information is provided, right? Yeah.
Yep. And also, if you're trying to use the product, find our documentation online. There's a bunch on dcp.dev. Sign up to the portal at distributed.computer and use it. We have an NPM package called dcp-client that you install in order to get going on Node.js. If you get stuck, we have a Slack. I think it's the Distributed Computer Slack channel.
Yeah.
Slack server, whatever they call it nowadays. I'm still an IRC guy. And go find us on there. There's a dev connection channel that actually links our internal Slack with that one. And that gets you access to my internal developers. So if if you get stuck and you need help, you've got the guys writing the product right there to help you out. And in terms of academia, we're actually working very heavily with a few different institutions right now. We have DCP deployed on a number of university campuses so that they can do compute work where they need it. And we're also doing research with Queen's University on distributed computing, and we're also doing student projects as well. I get interns from different universities on a regular basis. I actually had one from Waterloo last semester. Very, very bright young man. This is another thing that actually I really like about this job is I get to work, with people at the exact opposite end of their career than I'm at right now. And that is really exciting because they know different things, they want different things, and they want to learn. So these are the things that make me want to get out of bed in the morning and go to work, even on snowy days like today.
Yeah, I think we can all can attest to that. It's exciting problems, difficult problems like this, which excite us. But thank you. It was amazing, Wes and Hamada, for you to join and share the insights that you have built at King's distributed system. And thank you once again for being part of this. I will share all of this information in the description. So the Slack channel, access to the platform, if you give that, I'll update the description. If you wish to share the slides, please let me know. I'll make sure that I post a link in the description as well so people can review it later on. But thank you for being part of today's session. We look forward to incredible achievements in 2021.
Thank you very much. We're really looking forward to this year because, boy, things are about to start to take off down here.
Yeah. And thank you for our audience for joining live. And I hope to see you in the next session. That's going to be in 2 weeks' time. Thank you. Bye.